Good day. The topic we are discussing today is sum to infinity by Monserrat. In the previous lessons, we have discussed and obtained the sum of arithmetic progression and geometric progression to desired number of terms. So the aim of this lesson is to explain how to obtain the formula for obtaining the sum of an AP and GP for infinite number of n, if possible, and also to solve sample questions with the obtained formula or formulae. Before we proceed into this topic, certain topics such as the formula for the sum of the first n terms of an arithmetic progression and geometric progression, identification of the first term of an arithmetic progression and geometric progression, how to obtain the common difference of an arithmetic progression, how to obtain the common ratio of a geometric progression, limits, absolute value, and combination of inequalities must have been known by the viewer of this video, so that by the end of the lesson, you will be able to obtain the sum of an infinite AP, the sum of an AP that has infinite term, or a GP that has infinite terms, if possible. So now we move to how we got the formula for either the sum of an AP to infinity or sum of a geometric progression to infinity. So we have three equations here. We have equation 1, which is the formula for obtaining the sum of first n terms of an arithmetic progression. A is the first term, D is the common difference, and n is the number of terms, that is if you have a finite term. Equation 2a is the formula for obtaining the sum of the first n terms of the geometric progression for the condition absolute value of r greater than 1. And equation 2b is also the formula for obtaining the sum of the first n terms of a geometric progression for absolute value of r less than 1. Here r is the common ratio, a is the first term, and n is the number of terms, that is when we are dealing with a finite number of terms. But in this particular video, we want to discuss the situation whereby n here will tend to infinity. N will be a very large number. Infinity is something that has no bound. It has no upper bound or lower bound. It's open. Infinity can be a very large number that maybe you can imagine, but you may not be able to solve for it here. Like if you have 300 million terms, you can see that 300 million is a very large number. So now in this lesson, we try to check if we can obtain the sum to infinity for an AP. We try to also check if you can get the sum to infinity for a GP for this condition or for this condition. So now, if n tends to infinity, that is if we continue to increase the value of n, maybe if we continue to increase from 1 to 2 up to 500 up to 1000, you can see that the value is increasing and it is moving towards positive infinity. So we want to check what will happen to equation 1, which is the sum of the first n terms of an AP, and equation 2a and 2b, which is the sum of the first n terms of a GP, this one for absolute value of r greater than 1, and this for absolute value of r less than 1. So let's go and test with some values with varying values of n. So now we start from the first equation. In the first equation, we are going to take an assumed value for a and d and also vary the values of n in ascending order. So here we choose the value of a to be 2, that is, we assume the value of a to be 2 and d to be 4. We want to test that as n increases, what will happen to s subscript n, which is the sum, the value of the sum of that particular number of 10. So now we test with values of n, 4, 7 and 10. So now let's start with when n is 4. We already have the assumed value of a to be 2 and assumed value of d to be 4. So S4 will now be equals to 4 over 2 into 2 multiplied by 2 plus 4 minus 1 multiplied by 4. So if that is evaluated, we get the value of S4 to be equals to 32. So you can see that when n is 4, xn is 32. So now let's increase the value of n to 7. So we have S7 equals 7 over 2 into 2 multiplied by 2 plus 7 minus 1 multiplied by 4. If that is evaluated, we have 98. We can see that when we increase the value of n from 4 to 7, the value of Sn increases from 32 to 98. So let's test with another value of n, that is, let's increase the value of n from 7 to 10. So we have 10 over 2 into 2 multiplied by 2 plus 10 minus 1 multiplied by 4. If that is evaluated, we get S10 to be equals to 200. So you can see that as we are increasing the value of n, that is, when we increase the value of n from 4 to 7 to 10, the value of Sn is also increasing. So as n increases, the value of Sn increases. So as n gets larger, the value of Sn also becomes very large. So we can't have a particular formula for obtaining the sum to infinity of an arithmetic progression. So the sum to infinity of an arithmetic progression does not exist, since as n increases, the value of Sn also tends towards infinity. So if you have n to be 5,000, the value of Sn2 will be very, very large. So as n tends to infinity, the value of Sn also tends to infinity, thereby making it impossible for us to get a particular formula for obtaining the sum to infinity of an arithmetic progression. So now we move to the sum of the first n terms of a geometric progression for absolute value of r greater than 1. So let's explain this particular statement, absolute value of r greater than 1. This means, when a particular number is under the absolute value sign, it's usually in two forms. You have the positive part and the negative part. So this statement means that it's either positive r greater than 1 or negative r greater than 1. So if positive r greater than 1, that can be written as r greater than 1. And if negative r is greater than 1, we are looking for ordinary r, not negative r. So we divide both sides by the coefficient of r there, which is -1. So the moment you divide by a negative number, if you are very conversant with inequalities, the inequality sign will change to its opposite form. Here we have greater than. The moment we divide by -1, it changes to less than. So r will be less than 1 divided by -1 will be -1. So here, this particular statement can also be written as for r greater than 1 or r less than -1. And that cannot be combined. They say r greater than 1, that is, r is positive, and r less than -1, and also r is negative. so there is no way we can combine the two inequalities. So here we test for two conditions. The first one is when r greater than 1, and the second condition is when r less than -1. So also here we have an assumed value of a and r, and we vary the value of n in ascending order. So here we assume, since for the first condition the value of r must be greater than 1, so we take the value of a to be 2 and the value of r to be 2 also. So we vary the value of n from 2 to 6 and from 6 to 10. So when we vary it, we observe what happens to the value of Sn as n increases and the value of r raised to power n as n increases. So now for n equals 2, we have S2, which equals to 2 into 2 raised to power 2 minus 1 over 2 minus 1, and if that is evaluated, we have the value of Sn to be 6 and the value of r raised to power n to be 4. So when n is 6, we have S6 equals 2 into bracket 2 raised to power 6 minus 1 over 2 minus 1. If that is evaluated, we have the value of Sn to be 126 and the value of r raised to power n for that particular number of n, that is 6, to be 2 raised to power 6, which is 64. So now when we increase the value of n from 6 to 10, S10 will be 2 into bracket 2 raised to power 10 minus 1 over 2 minus 1. If that is evaluated, we have 2046, and the value of r raised to power n, which is 2 raised to power 10, is 1024. So from this result, that is when n is equals to 2, we have the value of Sn to be 6 and r raised to power n to be 4. When n is 6, we have the value of Sn to be 126 and r raised to power n to be equals to 64. And when n is 10, we have the value of Sn to be 2046 and r raised to power n is 1024. So we can see that from this result, it's observed that as n increases, the value of Sn and r raised to power n also increases. So we concluded that if n becomes arbitrarily large, the value of Sn2 will become larger and the value of r raised to power n2 will increase as n increases. So this, as n tends to infinity, the value of r raised to power n2 will move towards infinity. As n increases, the value of r raised to power n increases, so it will also move towards positive infinity. And infinity minus 1 will also give a very large number, multiply by this, divide by this, so Sn2 will be arbitrarily large. So there is no way we can have a particular formula for this first condition, that is for r greater than 1. There can't be a particular formula for obtaining the sum to infinity of a GP. So now we move to the second part, which is r less than -1. That is, let's test when the value of the common ratio is less than -1. Maybe we can have a unique formula for obtaining the sum to infinity. Here we are now talking about GP. We have concluded that an AP does not have sum to infinity. So now we also retain the assumed value of A to be 2, but now we have to choose the value of R to be less than -1. So we assume that value of R is -2, and we also want to vary the value of n from 2 to 3, 4, 5, 6, and then 7. So we test what happens to r raised to power n and s. So now we start for n equals 2. We have S2 to be equals to 2 into -2 raised to power 2 minus 1 over -2 minus 1. If that is evaluated, we get the value of S2 to be equals to -2 and the value of r raised to power n to be equals to 4. When n is 3, we have 2 into -2 raised to power 3 minus 1 over -2 minus 1. The value of Sn is 6 and r raised to power n is 8. When n is 4, if you should substitute the value of a to be 2, r to be -2 and n to be 4 and evaluated, we have value of Sn to be equals to -10 and r raised to power n equals 16. When n is 5, the value of Sn equals 22 and r raised to power n equals -32. We know the value of a is 2 and r is -2. When n is 6, we have the value of Sn equals -42 and r raised to power n equals 64. When n is 7, the value of Sn equals 86 and r raised to power n equals -128. So now we have the result for the value of Sn for when n equals 2 to 7, and the value of r raised to power n for the varying values of n from 2 to 7. So now if we should look at this result, we observe that as n increases, that is, as it increases from 2 to 3 to 4 up to 7, the value of Sn tends towards negative infinity when n is even. That is, when n is 2, we have -2. When n is 4, we have -10. You can see that when n is an even number, it is decreasing from -2 to -10. When n is 6, we have -42. When n is, okay, that's the last even number we tested with. When n is 2, -2. When n is 4, -10, and when n is 6, we have -42. You can see that it is tending towards negative infinity. If you have n to be 50, it's going to give us a more smaller number. That is, it's tending towards negative infinity. That is why we said as n increases, the value of Sn tends towards negative infinity when n is an even number, and it tends, that is, the value of Sn tends towards positive infinity when n is an odd number. Let's check for that. When n is 8, we have the value of Sn to be equals to 6. You can see that 6 is a positive number. When n is 5, the value of Sn is 22. You can see that it's getting larger when n is odd. And when n is 7, the value of Sn is 86. So if n is a very large odd number, also the value of Sn2 will also be very large. That is, as n tends to infinity for odd numbers, the value of Sn also tends to infinity. So for that particular condition, r less than -1, the formula for obtaining sum to infinity also does not exist. And also, we said we are going to check what happens to r raised to power n too. R raised to power n tends to positive infinity when n is an even number, and it tends to negative infinity when n is an odd number. So since the value of Sn and r raised to power n tends to either positive infinity or negative infinity as n increases, therefore the formula for the sum to infinity for this particular condition does not exist. So this cannot give us the formula for sum to infinity of a geometric progression. So we are going to test for the second formula of sum of the first n terms of a geometric progression. We are going to check if we can get the formula for sum to infinity. So the first thing we are going to do here is explain this particular statement. Absolute value of r less than 1. So it's same procedure as this. We have two parts. The first part is positive r less than 1, which is same thing as r less than 1. And the second part is negative r less than 1. We are told here that we divide by the coefficient of negative r, which is -1, and if we should divide by a negative number, this sign will change from less than to greater than. So we have r greater than -1. So we can see that the two statements can be combined. The first one says r is less than 1. The second one says r is greater than -1. So we can see that -1 is less than r, but r is less than 1. So this particular statement can be written as -1 less r less 1. That is, the value, that is, r will take its value between -1 and 1. R can be half, r can be 1/3. So the value of r will be numbers between -1 and 1. So that is the meaning. These statements can be written as -1 less, strictly less than r, strictly less than 1. So now here also we take an assumed value for a and r, and we also vary the value of n, and we see what happens to the value of Sn if we can get the sum to infinity, and also what happens to r raised to power n. So now we take the value of a to be 2, the value of r to be half, and we test for the values of n, which are 2, 5, 7, and 10. So here, when n is 2, we have 2 into 1 minus half raised to power 2 over 1 minus half. If that is evaluated, the value of Sn will be 3, and r raised to power n will be 0.25, which is 1/4. So now, when we move to the next value of n, if n increases from 2 to 5, we have S5 equals 2 into 1 minus 2 minus half raised to power 5 over 1 minus half. If that is evaluated, the value of Sn will be 3.8, and the value of r raised to power n will be 1/32. So the next value of n is 7. That is, when n increases from 5 to 7, we have 2 into 1 minus 1/2 raised to power 7 over 1 minus 1/2. If that is evaluated, we have the value of Sn to be 3.97, and the value of r raised to power n is 1/128. Also, if now take the last value of n that we want to test here, which is 10, S10 will be a into 1 minus 1/2 raised to power 10 over 1 minus half. The value of Sn will be 3.99, and the value of r raised to power n will be 1/1024. So from the result, the value of Sn for n equals 2 is 3, and the value of r raised to power n is 1/4, or 0.25. When n is 5, the value of Sn equals 3.8, and the value of r raised to power n is 1/32, or 0.03125. When n is 7, the value of Sn is 3.97, and the value of r raised to power n is 1/128, which is same thing as 0.0078125. For the last value of n we are testing here, that is when n is 10, the value of Sn is 3.99, and the value of r raised to power n is 1/1024, which is also equals to 0.000977. So from the result, that is from the result we obtain from the values of Sn and r raised to power n as n increases, The observation made is that with varying values of n, the value of Sn is increasing, but the difference between them is very small. You can see that the value of Sn is within 3 point something. The first one is 3, the second one is 3.8, the third one is 3.97. You can see that the value between the difference between the values of Sn as n increases is very small. And also, as n increases, we can see that the value of r raised to power n is moving towards 0. The first value of r raised to power n is 0.25, the second value is 0.03125, the third one is 0.0078125. So if we have a very large n, we will see that r raised to power n will give us 0. Maybe 11 zeros before we can get a significant figure. So as n tends towards infinity, r raised to power n tends towards 0. So here we can see that when n is infinity, s infinity, we can take the value of r raised to power n to be 0. So since we are dealing with sum to infinity, when n is infinity, that is when n has when n has become a very large number, then as we've said before, as n tends to infinity, r raised to power n returns to 0. So we can write this as s infinity equals a into 1 minus 0 over 1 minus r, which is a multiplied by 1, a over 1 minus half. So we can see that this particular condition, that is for absolute value of r less than 1, or we say minus 1 less r less 1, give us a particular formula for obtaining the sum to infinity, and it only deals with a geometric progression. So this formula for sum to infinity now is a over 1 minus r. So that is how the formula for sum to infinity is derived. And the only condition for this particular formula is minus 1 less r less 1. That is the value, and r must take its value between minus 1 and 1. So now, this is just a summary of what we've been explaining. S subscript n in 1 and 2a will continually increase, that is Sn returns to infinity as n tends to infinity. Therefore, there is no limit to the sum of these two series, that is the one for sum of AP and sum of GP for absolute value of r greater than 1. But as n tends to infinity in 2b, that is when absolute value of r less than 1, r raised to power n tends to 0. Then Sn in 2b becomes s infinity, that is when n is very large. When n tends to infinity, r raised to power n will have become 0, and we have this formula. And the condition is for modulus of r less than 1, and that is tagged as equation 3. So therefore, equation 3 is the formula for obtaining the sum to infinity of a geometric progression for minus 1 less r less 1. So these are examples to demonstrate what we have been explaining. So some of the examples are from the past UTME questions, UTM 2002, 2012, 1998, 1992, and 2010. So in this particular video, we only solve for the solution of the first examples. The remaining example will be solved in the next video. In the first example, we were given a particular series 1 plus 1 over 3 plus 1 over 9 plus 1 over 27. So from the series, we know that the first term is 1, that is a is 1. If you are conversant with how to identify the first term of a geometric progression, you know that the value of a, which is the first term, is 1. So now To obtain the common ratio of the first series of the series, to obtain the common ratio is either you divide the second term of the series by the first term, which must be equal to dividing the third term by the second term, which must be equal to dividing the fourth term by the third term. These are the terms given in the series, so we can use any of this to obtain the common ratio. So if we should evaluate this, it must be equal to evaluating this, which must be equal to evaluating this. So if we should evaluate each of these, we get 1/3. 1/3 divided by 1 will give 1/3. 1/9 divided by 1/3 will give 1/3. 1/27 divided by 1/9 will give 1/3. So therefore, the common ratio, which is r, equals 1/3. Therefore, the first term a is 1 and the common ratio r is 1/3. So the next thing to do now is to obtain the sum to infinity of that particular series. So the formula for sum to infinity, as we have obtained, equals a over 1 minus r. So we now substitute the value of a, 1/1, minus the value of r, 1/3. 1 minus 1/3 will give 2/3. 1 divided by 2/3 is same thing as saying 1 times 3/2. And 1 times 3/2 will give 3/2. Therefore, the sum to infinity of the given series, that is this particular series, is 3/2. Next video will be more on sum to infinity with sample questions and solutions. Please subscribe to our YouTube channel, like and share our videos. Thank you.